The next things we want to talk about is the walk and path. If we plot out the PV plot for your system, we know we start from an initial state where the pressure is 5 atm. We end up with a final state where the pressure is actually 2 atm. And then we do these things under a constant temperature conditions. That means we are going to have an isosome go from the initial to the final state. So it should look something like this, going from your initial state to your final state. Can you actually calculate the walk based on this plot? The answer is depending on whether you have a reversible or irreversible processes. If your system is actually undergo a reversible processes, then yes, you can do it, right? Because your P external is going to equal to your P. Then the walk will be just the area under the curve, PdV. Okay, but if today I did not say it's undergo a reversible process, then this plot did not actually give you the walk you are going to get. The things that can really give you the walk will be your P external plotted against the V. Again, you start from 5, that's your initial state, undergo isothermal expansion, and at 2, okay, that's your final state. This plot will actually give you the amount of walk. Okay, it will be just your PdV, right? There will be actually this area. So to go from the figure on the left to the figure on the right, you should know that the condition you should have is actually if this is undergo a reversible process, then this two is actually equivalent. If today okay, I have P external 5 atm, P system 2 atm, I just let it go. I know I'm going to have a irreversible processes, right? So if you plot that situation, you will be more like this. Your P external, okay, start from 5 and at 2. Okay, so what's going to happen is actually you go from 5, P external is actually 5, you actually go down here, and then you change your volume. Therefore, the work you can do is this much. So you know the pressure will quickly reach 2 atm. So the work you do will be just simply this small area. Apparently you can see that's actually reversible, right? On the top and the irreversible at the bottom. Eventually actually reach the same final states. So from here you should see that for the reversible and irreversible, the amount of work you do to the system will be very different, right? Because for the irreversible, you only do this much of work. But for the reversible, because it actually increase your pressure step by step. Therefore, the work is actually a lot. For the reversible processes, you are going to get the maximum amount of work. So maximum, we need to put quotations here. I'm going to explain very soon. But the things I want to say again is actually, assuming today you have this, okay, you know your P external. Okay, this is actually the things that's close to your real life experience. Can you actually get back to this? Can you actually plot out the PV for your system? The only thing you can do is actually you can know the initial state. You can know the final state. But anything else, you don't know. Okay, because you're on the irreversible process, that means actually you cannot calculate anything in between your initial and final state, right? Therefore, you don't know how the system is going from the initial to the final state. What people really do is actually, okay, since we don't know, we don't draw solid lines. Instead, we just draw some dashed lines to represent that we know the system is going to go from the initial to the final state, but we really don't know how you actually get there. So this kind of notation you need to actually get familiar with. All right, so let's talk about this maximum amount of work. Here, you can think about for the reversible step, that's the total amount of work you have done. And then for the irreversible, it's much less. So it makes sense that for the reversible work, always give you the maximum amount of work. Okay, but this is only true when you undergo the compression. If today you're actually doing the reverse one, for example, your initial P system is 5, okay? Your P external is only 2. Because your system has larger or higher pressure than your surrounding, it's going to expand. So when you expand, the plot will look like this. Let's plot out the irreversible plot first. This is 5, this is 2. Your initial will be still 5, your final will be 2. But here is actually you maintain 5 in the beginning, and then you go to your 2 in the end. So you go from your initial to your final state. So under this case, it's actually not the maximum amount of work. Instead, it will be actually the minimum amount of work. Okay, so depending on its actual expansion or compression, you either get the maximum amount of work or the minimum amount of work. But the consensus is actually, it gives you the extreme values. Okay, either the maximum or the minimum amount of work. So those are the things that you should have in mind. If you have a reversible processes, it either give you the maximum amount or the minimum amount of work. All right, so the very last thing I want to talk about the work is actually the type of work. So far, we always talk about the dW equals to P external dV, right? So this is actually what we have. This is the only type of work you're going to encounter in the simple system. But if today you don't have simple system, that means actually you're going to have other type of work. For example, you actually blow a balloon, then you know when you blow the balloons, the work you do will actually related to the surface coefficient times the area you actually increase. Or you actually stretch a string, then the work you do is going to related to the force constant times the distance you stretch. This is actually surface coefficient. And then the F is actually the elastic coefficient. And then you can also do this for the charge times the number of charges you have. There are actually many different types of work can be involved. But so far for this chapter, we are going to stay with the simple system where we only discuss the system that the work can be actually achieved through the PdV. All the other things is not within our discussion. Okay, but you can see that if in the future you are doing some electrical chemistry, then you know in your work term these things need to be included. So it's actually expandable. Okay, but right now we just focus on a simple system. Then the calculation will be much easier. All right. Okay, so from the discussion so far, you should have an idea that is work path dependent or path independent? Dependent, right? It depending how you actually get to from your initial state to a final state, the work value will be very different. Okay, so remember we discussed what is the state function in the very beginning. That we say the state function is actually the parameters that we can use to describe the status of a system. And it only depending on the state. It doesn't matter how you go to your states. It only relates you to the specific states. So it's actually a path independent variable. So from this concept, you know the work is not going to be a useful state function because it's actually path dependent.